Welcome, class. This time, in this video, we're going to be talking a little bit about some common misconceptions that I often see that students have about the theory of evolution. When all of us hear about evolution, we have different responses to it, and often there's kind of some beliefs out there and some opinions of things that aren't really that accurate. So we want to address those today. And during my years of teaching about evolution, I've seen a lot of questions that students have or just friends and family members of mine have. And here's just a few examples, and maybe you've had these too. But what about, does the theory of evolution explain the formation of the Earth? It's kind of an interesting question. Obviously, many of us, when we think about evolution, we think about things very early on in life. What about, am I evolving as I age and grow now? Because I'm getting bigger, I'm getting older, some of us are getting uglier looking as we get older. Is that the type of change we mean when we say the theory of evolution? Shouldn't all species be perfect or more like humans if evolution is real? Right? Most of us kind of have this idea that evolution is making species better, and us as humans, we're pretty awesome, right? So shouldn't all species kind of be becoming more like us because we're the best, right? And that's kind of an interesting idea in itself that we can talk about. And then what about this? Did I come from monkeys? Another common question you get from people, and something that can sound quite offensive for someone that has a religious background and believes in a creator, that, hey, I didn't come from a monkey, all right? I'm nothing like a monkey. Even though some of us more or less kind of look like monkeys at times, right? So before we continue, I want you to think about this critical thinking question right here. And that's, what questions similar to these have you had about the theory of evolution, right? It could be something kind of similar. It could be something completely different. But I want you to think about, especially recently in your life, but what have I kind of struggled with, or what questions have I had about evolution? So spend about 30 seconds or a minute doing that. Okay, hopefully you came up with something pretty good, and I hope that at least at one time in your life, the idea of evolution has been on your mind and you've kind of wondered something interesting about it. So this is, of course, the main objective today then, is to dispel any of these myths or misconceptions that you've been taught or you've been told about the theory of evolution, and just give you guys a pretty good background before you start going more into some of the difficult aspects of evolution and learning more about the basic principles that govern it. Okay, so as I've been teaching the theory of evolution from religious universities and in the Deep South, the Bible Belt, right? I've kind of picked up on what I call the big 5 misconceptions, and there's many more than this. If you just Google evolution misconceptions, there's complete pages that go through and explain in detail about all of them, but I just want to break it down to what I consider the top 5 that I've seen most often. And this is the first one. Evolution is a theory about the origin of life. So we'll talk about that. And what you'll notice is that in each one of these statements, there's really probably only about one word that makes it a myth or a misconception. So in the first one, evolution is a theory about the origin of life. I would say that the word that's really not true there is origin. Okay? Everything else there is correct. I mean, when we're talking about evolution, it does have to do with living organisms, but not necessarily the origin of them. Number 2, natural selection involves organisms trying to adapt. So natural selection, the process that results in evolution, one of the processes, does have to do with adaptation, but it doesn't have anything to do with organisms trying. So we'll talk about that and why that's an incorrect statement. And what about this? Individual organisms can evolve during their lifetime. Now, of course, organisms can evolve, and we're going to talk about species evolution, but as I want to make really clear right now, and we can go into more detail in a few slides, is individuals do not evolve. Number 4, the goal of evolution is to progress towards becoming the perfect being or species. So actually, this one has a few words that make it a myth or a misconception. One is that there is no goal of evolution. Right? There's not some kind of like agenda or some kind of like ultimate pinnacle that evolution is trying to get to. And it definitely does not result in perfection. Right? It would be hard to claim that humans or any other species are perfect, and that's really not what the process of evolution is doing. And then this last one is, if humans came from chimpanzees, chimpanzees should be extinct. And so this is another one that we can talk about, but of course they're not extinct, even though there is pretty good evidence that we share a common ancestor back with them in the fossil record. So let's go through each one of these one by one and make sure we understand why these are misconceptions and not totally accurate about the theory of evolution. So what about this idea that evolution has to do with the origin of life? So what I did, just to give you a comparison, is I just Googled evolution to see what Google would say is the definition of evolution. So let's read this. The process by which different kinds of living organisms are thought to have developed and diversified from earlier forms during the history of life. So kind of just marinate on that for a second, soak it in. What does it tell you? What does it not say about evolution? And then also I decided to look up in the dictionary, right? Merriam-Webster. How do they define evolution? Descent with modification from pre-existing species. Cumulative inherited change in a population of organisms through time leading to the appearance of new forms. So one thing I really want to stress out are kind of some underlying forms here, some words here. So diversified from earlier forms, right? Or what about down in the dictionary? Pre-existing species. One thing that you'll notice is absent from both of these definitions is anything about the origin of living things or anything about the origin of the earth, right? So even though a lot of people, that might be the first thing that pops in their head when you say something about evolution, they might say, no. I believe that God created all living things, not that they evolved. So really though, when we talk more about the theory of evolution, it should become pretty clear that we're not actually talking about the origin of living things. We're talking about once living things evolved, once living things came to be, how did they change over time? And that's the process of evolution. So now, of course, during an evolution course, you might talk about the origin of living things to kind of give some backdrop into how we think living things started so that the process of evolution and natural selection began to operate. But really, the question of how did living things originate is more of a question of chemistry and physics and geology, which is kind of interesting. Okay, so let's move on to number 2. And you may recall that our second misconception had something to do with organisms trying to adapt, right? So let's talk about natural selection and adaptation. And to do that, I want to use 2 examples that I like that illustrate pretty well the concept of natural selection and how that results in evolution. And these are Darwin's finches, so a group of finches that live on the Galapagos Islands, and these cute little mice called rock pocket mice. So first, let's talk about Darwin's finches. Okay, so we have a figure over here on the side of the screen, and this is a pretty cool research project that a couple, Peter and Rosemary Grant, have been working on for decades. So there's these group of finches called the Darwin's finches, and starting back in the 70s, they started going out and collecting finches every year and measuring various aspects of their health. So they'd measure their size, their mass, and they'd measure different characteristics of the beak because they felt that the beak was a really important adaptation for their diet and how they survived on these various islands. So what we're looking at here is a particular year where they had a severe drought on the island. Okay? So you can see that this right here, the top part of the graph, is what the population looked like before the drought, and down here is what it looked like after the drought. And I also want to make sure that you pay attention to what the axes are here. So we're just looking at the number of individuals on the y-axis, that's pretty straightforward, and then we're looking at the bill or the beak depth in millimeters on the x-axis. Okay, so there should be a couple things that are really apparent when you first look at this. The first is that there's many more individuals before the drought as opposed to after the drought down at the bottom. Okay, so this was obviously pretty devastating for this population of finches, and most of them died. And you can see the little red triangles right here tell us what the average beak depth was before and after the drought. And the most important thing that I want you to see about this figure is that there's a shift. Okay? So whereas, the average beak depth might have been 9.7 before the drought, it ended up being 9.9 after the drought. And you may look at that and say, well, that doesn't seem like a whole lot, but that actually is a significant difference. Okay? Now, if we look at this situation and we say, okay, we measured the birds before the drought and we measured them after, and there seems to be this shift in the average bill depth, the population must have evolved. And I would argue that not quite yet, because something that's really important for to define evolution is it's that a change in a species over generations. Well, this example that we've been using so far is just within the same generation. All that happened is on average, the birds with the smaller beaks died, and the birds with the larger beaks survived. So we see this shift. But the scientists actually did follow this for future generations. And it turns out that these individuals over here with larger beaks produced offspring with larger beaks. And so we actually did witness a shift in beak depth size over the course of generations. So that is a pretty good example of, there was no organisms trying to adapt here. What we saw was a shift in the population from one mean to a different mean based on the environmental conditions. So let me make it real clear what did not happen, right? So I just want to make sure that this is an incorrect example. This is not what happened. So you can imagine that these finches are hanging out and like there's a drought, there's no water, there's not really much to eat. The only thing that there is to eat are these larger seeds, right? But you need a pretty big beak to crack these larger seeds. And so an incorrect example would be to think that the birds all of a sudden like, oh, I really need a bigger beak. And they just like concentrate on it and they work on it and poof, they get a bigger beak, or they eat something that gives them a bigger beak. Okay, that's why it's a myth that organisms are trying to adapt. Okay, there's no trying to change your beak size or anything like that. The process of natural selection results in that mean shift of the population, but not individual birds. Okay, so let's move on to the rock pocket mouse and see how this could be another example where we can see natural selection occurring, but where organisms aren't trying to adapt. So these are cute little mice. They're in the state of New Mexico, and specifically the area that I'm going to talk about that's a part of their habitat is the Valley of Fire, New Mexico. And something interesting about the Valley of Fire is that thousands of years ago there was a series of volcanic eruptions that created these lava flows, right? So most of the environment is kind of this tannish brown desert, but you have large patches of these lava flows where the environment is now dark, almost black. And you have the rock pocket mouse that inhabits both of these areas. So you might imagine that in the desert, this mouse right here, he blends in pretty well, right? He's pretty much the same color as environment, might hide him pretty well from any type of predators that I'll mention in a second. But this mouse would probably not do so well on a lava flow. He might stand out like a sore thumb and not do so well. But what scientists that study these rock pocket mice have noticed is that over the course of evolution, there's actually two different variants of this mouse now. And they're both the same species, but one of them has light fur and one of them has darker fur. And I've kind of represented that here by these triangles. Okay, so the darker triangles would be the darker fur rock pocket mouse, and the lighter ones would be the lighter fur. And you can see what I've done here is just kind of create two different basic environments. Over here we have the typical desert of the Valley of Fire, and to the side here we have a lava flow. Okay, now obviously they're not normally perfect rectangles, but it works for this example. Now you can imagine that most of the predators of these mice are visual predators. Okay? So they're hawks, snakes, eagles, in this case a horned owl that I put up a picture of here. And they're going to be hunting visually. So you can almost, especially even if you just squint your eyes as you're looking at this slide, you'll see as a visual predator which ones would probably be most likely the mice that you would eat. So if they're hunting on the lava flow, then the easiest ones to be eaten are probably going to be some of these light ones. And if they're hunting in the desert, well, these darker colored mice are probably going to stand out a little bit more. And so over time, you would expect to get a scenario like this, where you have light colored mice in the light environment and dark colored mice in the dark environment. And the interesting thing is that's exactly what we see. So scientists that go and they capture these mice, it's gotten to the point now where almost always when they're capturing mice in the light environment, they catch light colored mice. And when they're capturing mice in the dark colored environment, it's always dark mice. So once again, are the mice trying to adapt? Was there any type of, there's these lava flows, but if I go over there, I'm probably going to get eaten, so maybe I should try to get darker fur, right? The organisms aren't inherently trying to do anything. But through the process of mutation, and scientists have actually figured all this out, what the exact mutation is, but a random mutation led to the coloration, the dark coloration that some of these mice have. And then over time, you can see from my little example that that is how the population evolved into becoming these two different colors, as one does well in one environment and one does well in the other, without the organisms trying to adapt to any type of situation. Okay, so let's think back to our finch example of the Galapagos, and let's look at this true or false question. We would expect the average bill depth of the species to continue to increase every year. Explain your reasoning. So I'll give you a few seconds to do that. Okay, so let's think about this problem a little bit. There's a couple different ways to look at it. Somebody might say, well, they got larger because of the drought, but if there's no more droughts, then I'd expect it just kind of to stay the same. Or you might look at it and say, well, obviously a bigger depth bill, a bigger bill is probably better. So maybe we should just expect to keep it seeing going on and on and on. Or you might look at it and say, well, it seems like, before the drought there was a certain beak size, so maybe it's going to go back to that eventually. There's some type of equilibrium. And there's lots of different things we can talk about, but in general, this question is going to be false. Okay? And this is going to be something we're going to talk about a little bit later as we go on, but just because bigger depths, bigger beak depths was better for 1 year, doesn't necessarily mean that it's going to be better to get bigger and bigger and bigger all the time. There's obviously some type of trade-offs and restraints and limitations to how big a beak can get, and bigger isn't necessarily always better. You can imagine a situation where all of a sudden now there's a plenitude of worms on the island, and if you have this huge beak, you're not very good at capturing the worms, but the small-beaked individuals do. So it's false. You're not always necessarily just going to expect to get increasing, because bigger isn't necessarily always better. Okay, so what about this idea of, am I evolving as I change and get larger? And I'll repeat it many times, but populations evolve, individuals do not. And I think since we're already talking about these cute little birds, let's keep talking about the finches and use them as an example. And I probably already said this, but I want to make it sure it's really clear before, is that of course these birds are growing bigger beaks as they get larger, right? But even if you imagine the adults that have pretty much reached full size, they're not going to be growing much more, especially in terms of their beaks. That's not what we're seeing here, right? That's not where this shift came from. We didn't have individual birds just getting larger beaks, okay? It just so happens in this example that the birds with the smaller beaks just didn't do so well, okay? They were less likely to survive. The birds with the larger beaks did much better. They were more likely to survive. So if we were to measure individual birds over this time period, it probably wouldn't change much, and it probably wouldn't explain the shift we see. But when you take the average of the population, that's where we see the shift and what we would explain as the process of natural selection. So really important that we're talking about a population or a species when we talk about natural selection, not individuals. Now I will clarify that we can say that natural selection acts on individuals, right? So the particular traits you have in your environment are going to cause you to be more likely or less likely to survive and reproduce. But when we talk about the evolution of a group of organisms, it's not the individual that's evolving, it's the population. Okay, and so let's think about this idea. I got this cool chimp here. He looks like he's smoking a cigarette, playing a guitar, right? He's probably got some good music. A common misconception is, there's a goal with evolution. It's to become the perfect species. And that's obviously what humans have done because we're so intelligent and we have the culture and we have these really complex nervous systems. So, maybe chimpanzees are going to be like that eventually too. Or the other thing I kind of have on the other side of the slide is, shouldn't we be evolving resistance to like these really serious diseases that seem to kill so many people? Why haven't we, through the process of natural selection, evolved resistance to them? So before I go into more detail, I would like to ask you a true or false question. And that is, if natural selection is operating, we would expect chimpanzees to become more human-like over time. And I want you to explain your reasoning. So take a minute and write that down. Okay, so let's try to think through this one, because this is one I see a lot, and rightfully so. I kind of understand where some people are coming from when they have this type of opinion. But in general, this is going to be false, right? And let's go back to our images of our cool rock star chimpanzee and cancer to talk about these. So the first thing I want you to think about is, this is going to be more obvious on the next slide, but early scientists often thought that evolution worked as a ladder, that you were kind of going up this ladder, and at the top you had God, and below him were angels and humans, and wild animals and domestic animals and plants and microorganisms, and they're all kind of based on this scale of hierarchy, and that we were all kind of progressing to become up towards the top, right? But Darwin proposed that actually evolution more works like a branching tree, right? And so that's what I want you to think about, is evolution is a branching tree, not a ladder that has some type of progression towards a goal. I think the best example I could give you to try to think of whether chimpanzees are trying to become more perfect or trying to be like humans is to think about their environment. So let's think about their environment in Africa, for example. So let's imagine we could run an experiment. You probably don't like this experiment, but let's drop a chimpanzee and you off in the middle of the rainforest in Africa, right? And let's just let you guys go for a few years, and we'll follow you and see who the most likely to survive in that scenario is, in that environment, right? So pretty quickly it's obvious that you are not going to do as well as a chimpanzee at surviving, right? Like maybe you're like Bear Grylls or whatever, and you're like, no, I got this, okay? But you can imagine in general putting a human individual with our adaptations and our characteristics in their environment that we're probably not going to do as well, right? And you could think of it as vice versa for a chimpanzee in human culture, even though some people have tried to do that. So evolution isn't about trying to become perfect or trying to be like humans. The goal of natural selection and evolution is to be the best adapted to your environment, right? So what that means is that as the environment changes, you might change as well. Kind of going back to the example I gave of the finches, right? That you could expect that during times of drought, we would see this shift towards larger beaks as we do. But you know what? These scientists that have followed them for decades, what they've seen is then when it starts to rain again, it's not so much advantageous to be able to have this large beak. You can save resources, put them other places, or it might actually be advantageous to have a smaller beak. You actually get a shift back in the other directions towards smaller beaks. So you would expect to see the same thing with chimpanzees. They are still evolving, and they're going to be changing through the process of natural selection, but they're going to be changing in a way that helps them be adapted to their own environment, not necessarily to what we think is an ideal environment or what evolution should look like. And then the other aspect of this is, severe diseases like cancer. Why haven't we just evolved resistance to them? And the one thing I will really stress here is that natural selection isn't about becoming more comfortable or about being stronger or anything like that. The way that natural selection works is through survival and reproduction. And the big one is reproduction, right? So you can imagine, I want you to imagine that you're like the awesomest individual to ever walk this planet. And maybe you are, right? Maybe you're sitting there like, this sounds like me, Dr. Tucker. Okay, so you are super strong. You can run miles without getting tired. You eat super healthy. Whatever you can imagine. You lift tons of weights. You're awesome at sports. Okay? But I want you to imagine the scenario that you have 0 children, right? But you're awesome. You live to be 120 years old. You have some amazing genes that have allowed you to do this. Okay? But guess what? What is your fitness, or in terms of natural selection, if it's all said and done and you have 0 children, it's 0, right? So natural selection isn't just about making us faster or healthier or anything like that. Natural selection is only going to operate on what makes you more likely to survive, and the big thing is reproduce, okay? So what you will notice about many diseases, such as cancer in this case, when does cancer most often strike human beings? It's later in life, after their reproductive years. Right? So of course you can get cancer before that, but most people are going to get cancer in their 50s, 60s, and 70s when they've already decided and had all their children, right? They've already had 3, 4 children. Okay, so does getting cancer when you're 50 years old reduce your fitness? It doesn't at all. So kind of think about that when you think about diseases that affect us after our reproductive years. they actually should not be influenced by natural selection because natural selection is only going to be based on our reproductive effort. All right, and then our last one is primate evolution. And, did I come from monkeys? Or, if we came from chimpanzees or apes, shouldn't they be extinct? So let me talk about those two things. So for the first question, let's look at this phylogenetic tree here. So that's what we call these trees that show the evolutionary relationships among organisms. And there's some interesting things here. So you can see, first of all, if you say, well, did I come from monkeys? Not really. So monkeys are way over here on this part of the tree. Okay, we can't even see most of the old world and new world monkeys. But we've been evolving separately from them for like 40, 50 million years, even more. Okay? So if someone ever says, did I come from monkeys? You can say, nope. Right? And if they don't know what a monkey is, you can tell them to go to a zoo, right? Monkeys are very different from apes. The easiest thing to tell them apart is that monkeys have tails, right? So we are most closely related to apes. And you can see more specifically, here's us. Okay, so, we got humans, we got an awesome looking Darwin right there. And you can see that the way that these trees work is that our closest relatives are the bonobos and the chimpanzees. And we share a common ancestor with them right here, right? And that is actually the proper way to talk about the relationships of us and to other primates, is not that we came from chimpanzees, okay? But it's that we share a common ancestor with chimpanzees. Somewhere between 5 to 8 million years ago are the best estimates, which means that we've been evolving separately from them for that long, right? And of course, in here with humans are other human-like hominins, like Neanderthals and some other species that you've heard about. And then there was another speciation event where bonobos and chimpanzees later actually split into their two different species. Okay, so what about us, coming from chimpanzees, and shouldn't they be extinct if that's the case? So that is more dealing with this figure down here. And I had a friend that actually said that to me one time. He said, I think he knew I taught evolution at the time, and he said, I saw this thing on Facebook the other day and it made total sense, right? It said, there's no way that evolution could be real because if we came from chimpanzees, then chimpanzees shouldn't still exist, right? And I had to kind of start to, okay, that's not how it works, right? It's a common misconception. Going back to this idea of being a ladder or a branching tree, right? So the way that evolution works is through a branching diagram. So we have a particular species, and through the process of speciation, it separates into two or more species. And I said, so of course, chimpanzees have been around, but there was at one point we shared a common ancestor with them, but then it split back here at this part of the tree, and now we've been evolving separately from them for 8 million years. So that's actually why I don't really like these diagrams, even though I know they mean well. Okay, but it makes it look like there's some type of progression, right? Like there was a progression from monkeys to apes to maybe hominins like Neanderthals, eventually till you get up to humans. And we do have sometimes changes within a species like that. But when we talk about these various primate species, this is what we should be thinking about in terms of how species change over time, is through this branching speciation, not that chimpanzees turned into us, but that we diverged from them 7 million years ago, and they've been evolving separately, and we've been evolving separately through natural selection and other evolutionary processes. So I appreciate your time, and I look forward to meeting with you next time.